So welcome everyone. My name is Shtub, and today I'll talk about advanced data modeling in NoSQL databases. Few words about me. So I lead the training at ScyllaDB. I'm a software engineer and I am based in Israel. I've been with ScyllaDB for quite a while, about 6 years. So I see there are questions in the chat window. The recording will be available and we will share a link to the recording with you, to all the people that registered. So I will also share the slides and links to the recording and to the labs that you're going to see. Okay, so you don't need to worry about recording it or making notes or copying links or whatever. We'll share the slides. Another thing before I start is that this is live. I would like it to be as interactive as possible. So feel free to ask questions using two monitors, looking at the chat window in the other monitor. Tell me if I'm going too fast or too slow, if it's boring, if you have any questions. I want to make it as interactive as possible. Okay, so there is quite a lot of material I want to cover. Like I said, the topic is advanced data modeling, but to go through to advanced data modeling, we need to understand the architecture of the database and some basic data modeling. So yeah, I want to see what's your previous knowledge and how much you need me to go through the more basic stuff. And I prepared quite a lot of slides, so it's about 80 slides. We won't have time to go over all of them. I also want to show you some hands-on, but I'll also point you to where you can find more information and learn more. Okay, so before I start, two very useful resources that you can use. One is ScyllaDB University. That's university.scylladb.com. And there you have a whole bunch of online courses and lessons, including slides, recordings, hands-on labs that you can run, quizzes, and so on. It's completely free. And to get started, all you have to do is register a user and get started. And all of the material that I will be covering today is also covered in ScyllaDB University. So check that out. It's self-paced, and that means that you can, whenever you have some free time, you can just take a lesson, stop and continue whenever you have time. The second resource is our documentation website, and that's docs.scylladb.com. And there you have more in-depth explanations, different procedures, how to add a node, remove a node, set up a cluster, and so on, installation instructions, and other manuals. So keep that in mind. And I'll start with a few words about ScyllaDB. I'll say that all of the material that I will be covering today is relevant for other NoSQL databases as well, specifically Apache Cassandra and Amazon DynamoDB, but also others. So there are a whole bunch of different data models for NoSQL databases. I won't cover the different types, but there are a whole lot of different use cases. So I'm going to be using ScyllaDB as the database to explain the different concepts that I will be talking about. So a few words about ScyllaDB. ScyllaDB is a NoSQL distributed database. It's open source, and we have a few different options for how to use it. Some of the main attributes of the database are high availability, and that means that, as I mentioned, it's distributed. It runs on multiple nodes on different computers at different locations, and it works with built-in redundancy. So data is replicated, and the database holds multiple copies of each piece of data. And that means that even if a node or even an entire data center goes down and becomes unavailable, or there is a network failure, the database can still serve requests. It's also highly scalable, meaning that we can add or remove nodes as the database is running without any downtime. And it's built for very high performance, and that means a high throughput. I'm going to share a link for a 1 million operations per second demo. And actually, that's not such a big number. We have customers running 1 billion ops per second, and they're running it at just single milliseconds latencies per query. So it's very fast and very high throughput. And you can see some of our users and customers here, some names that you're probably familiar with and others. Another attribute is low maintenance, so different auto-tuning features. And the database is a drop-in replacement, both for Apache Cassandra and for Amazon DynamoDB, which means that if you have an existing application that's using either one of those databases, you can pretty much run your application as it is and just change the underlying database to ScyllaDB and get a whole bunch of benefits, which I'll show an example of in just a second. So it's the next slide. So here we have a comparison of running ScyllaDB versus other databases. I don't really want to go into the details. You can find the full benchmarks, even with instructions for how to run it yourself and recreate it, if that's your thing. That's on our website. You can find it. But just an example from one of our users when compared to Apache Cassandra, they switched from 40 Cassandra nodes to 4 Scylla nodes, and they got times 11 better latency, while also reducing the cost by 2.5. So much lower total cost of ownership, less nodes means that it's way easier to maintain, and also better performance, which is important for many applications. Again, this is out of scope for this talk, but we have different options for how to migrate existing data. If you're working with CockroachDB or Bigtable or Postgres, you can migrate your data. Okay, and this is the demo that I mentioned that shows running 1 million operations per second on an i4i 8x large AWS machine. And I provide the link here, and you can run it yourself. What you're seeing here is our monitoring dashboard. If I have time, I'll also show it to you in the labs. And you can see that it's running 1.1 million operations per second. And the 99th percentile is below 1 millisecond. So it's very fast. Okay, so that's a good question. And Eran is asking if there's a hosted service or should we self-host? And that's a good question because I have a slide about it. So I'll answer in just a slide or two. But I also talked for quite a bit, so I just want to make sure people are still with me. If you can answer a quick poll question in the chat window. And the question is, what's your NoSQL status? I haven't heard about NoSQL. I heard about it, but I've never used it before, or I've used or am using NoSQL databases. If you can quickly write that in the chat window. Again, what's your NoSQL status? Just so I get an idea of who I'm talking about, who I'm talking with, sorry. Okay, so I see some people heard about NoSQL but haven't used it. Others have used it before, but not requiring complex data structures. Some come from an SQL background, which is good to know. Okay, so appreciate the answers. And again, maybe you missed the beginning of the talk. I said that this talk is live and I want to make it as interactive as possible. So feel free to ask questions in the chat window. I'm checking it every once in a while. And tell me if I'm going too fast or too slow. Okay, so that brings me to the question if I should go over some architecture and basic data modeling. So let me go over it quickly so we can move over to more advanced stuff. But before that, there was a question by Ivan, and I want to make sure that... Okay, so I don't see that I have the slides, so let me answer that one first. Okay, so the question was about ScyllaDB, and is it hosted or does it run as a service? And that's a good question. I didn't mention it, but there are different options. So ScyllaDB is open source. You can compile it and run it yourself if that's your thing. But we also have a database as a service offering called ScyllaDB Cloud. And with that, you get the database as a service. We take care of installation, performance, security hardening, upgrades, backups, repairs, and all of those other things so that you can focus on your core business, which is probably not administrating a database. So that's one option, ScyllaDB Cloud. Another, as I've said, you can run it on your own as open source software. You can also add features or open issues or send pull requests, again, if that's your thing. And we also have another option, which is ScyllaDB Enterprise, which is a production-ready version that comes with more features than the open source version. It's more stable and it has some better performance. And that also comes with our 24/7 support. And that can run either on the cloud or on-prem. Okay, so it's quite flexible. It's completely up to you. And if you want to play around with a cluster, you can start a free trial cluster on ScyllaDB Cloud. Let me write the link on the chat window. So it's cloud.scylladb.com. And with just a few clicks, you get a trial cluster up and running, and you can run the labs that you're going to see in just a bit on that trial. Okay. So there is a question, what are the pros and cons from self-hosting option in regards to scaling, and can the enterprise option be self-hosted? So the enterprise option can be self-hosted if that's what you choose, but it can also be run on different clouds. I didn't mention it, but we're not cloud specific. So we have users running it on AWS, GCP, Azure, and others, and also on some local clouds. So it's very flexible in that regard. And there's another question, what are the pros and cons self-hosting in regards to scaling? So the only difference that comes to mind is that scaling is something that is very easy. It's done by the user. And if you choose to use Scylla Cloud, then our team can do that for you. Otherwise, if you choose to self-host or to use Scylla open source, then you have to go through the procedure of adding a node yourself, which is very straightforward. You can find examples of that on Scylla University. But if you want the managed service, then we take care of that for you. So yes, Scylla is open source. I believe it's the AGPL license. And you can look at the source code, you can send pull requests and play around with that. It's written in C++. Okay, so let me move forward with some basic concepts. I'll try to go through this fast, but again, tell me if I'm going too fast. So I mentioned that Scylla runs on multiple nodes. It's a distributed database, and the basic unit that we talk about is a node. But what is a node? A node is the ScyllaDB software that's running on a computer, on a machine. And nodes work together to provide service to the users and answer queries. And together they form a cluster. We think about it as a node ring, like you see here, a node ring with 5 nodes. In production, we have, we recommend to have at least 3 nodes. And it can be all the way up to hundreds of nodes. We have some customers running huge clusters with hundreds of nodes. As I mentioned, data is replicated between the nodes. So for each piece of data, that data will be copied multiple times to different nodes, and the number of copies is determined by something called the replication factor, abbreviated as RF. And replication factor simply means number of nodes where data are replicated. Okay, this is something that's done automatically by the database. So as a user, when you insert a row, you don't have to worry about the replication. But it's important for you to know that data is being replicated under the hood. And as a user, you would determine the replication factor when you define a key space. A key space is a container of tables. In ScyllaDB, we have rows and columns. So we talk about tables. And if, for example, we define a replication factor of 3, like you can see in this example, then each piece of data is copied to 3 different nodes. And let's look at this quick animation. So we have 5 nodes in our cluster. Replication factor was defined to be 3. It could have been defined to be 1 or 5. Of course, there are trade-offs between the different options. And let's see what happens when we write data. Say our data is this orange cube. So it's automatically replicated to the 3 different replica nodes. And so on, and so on. And the same thing would happen when we read data. So 3 different nodes would hold this piece of data. Oh, okay. So just making sure you can see my slides. And this replication goes together. If you remember at the very beginning, I mentioned that ScyllaDB, as well as Apache Cassandra and DynamoDB, offer high availability. And that means that, say, one of our nodes, node 2, is unavailable. It goes down for whatever reason. The computer crashes, there's an earthquake, or I don't know, there's a fire. Then our database would still be able to serve requests because all the data in node 2 is replicated on some other replica nodes. Okay, so it's easy to understand that if we set a higher replication factor, we're going to have higher availability. However, there are always trade-offs and it doesn't come for free. So it would require more hardware, and there also might be an impact on performance. Okay, that really depends on your use case, but it doesn't come for free. So there is a request to run the application again. Let me do that. So I hope you can see it now. I am looking at a 5-node cluster, and whenever I write data, the data is automatically replicated to 3 different clusters. And in the next slide, I will explain how that replication happens under the hood. Okay, great. So what happens under the hood? Again, I'm explaining this not because you have to do it as a user, but because it's important for you to understand how it's done and how the database works in order for you to understand more advanced data modeling concepts. So in ScyllaDB, as well as in Apache Cassandra and DynamoDB, we have something called the partition key. And the partition key is 1 or more columns in our table that has a special role. And according to the partition key, the database knows which nodes are responsible for that piece of data. So how does that work? Here I'm showing you an example of a very simple table that has just 3 columns, the pet chip ID, the time, and the heart rate. And in this case, the pet chip ID is defined as the partition key. So this column is the partition key. And say we want to write a row, say the first row, what the database does under the hood is it performs a consistent hash function on the partition key. And according to the hash, it knows which replica nodes are responsible for that given row. Okay, so this happens very fast, just running the hash function, and it immediately knows which node is responsible for that specific piece of data. Now, let's go over a few more concepts that I keep talking about, but I didn't really explain. So I mentioned a key space. A key space is a container of tables. Some applications have just one key space, but some applications have more than one key space. And the most important settings that are determined for the key space are the replication factor. Within a key space, we have tables. A table, just like you would think of it, has rows and columns. And maybe the two most important settings that we define for each table is the partition key, which I just talked about. And another one is the clustering key, which I'll talk about in just a minute. Okay, another important concept is consistency level, so also abbreviated as CL. And I mentioned that when we write data, it's replicated to the different replicas according to the replication factor. But when we perform a query, in order for it to be successful, it needs to meet a certain consistency level requirement. So the definition of the consistency level is the number of nodes that must acknowledge a read or a write request. And some possible values are 1, quorum, local quorum, or all. And the consistency level is set per operation. So in my application, maybe I have some operations that say I'm recording the temperature in the room every second, and I write that to the database every second, every second, every second. So maybe the consistency level is not that important because even if I miss 1 second, it's not that big of a deal. So for the write query, I can set a consistency level which is a bit lower, say 1. But maybe when I read the data every hour, I want the reading to be very accurate, and then I would set a higher consistency level. Okay, now what exactly does this mean? I don't have a slide for it here. Maybe I'll go to the end, and here I have a slide for it. Okay, so let's look at an example of what happens when we write data. In this example, we have 5 nodes, as you can see, a replication factor of 3, and the consistency level is quorum, meaning that a majority of the nodes have to respond in order for the query to be successful. And that's a majority out of the replicas. So a majority out of 3 replica nodes would be 2. So I write the data, let's call the data 1, just to simplify things. So the client writes the data to one of the nodes. In ScyllaDB, any one of the nodes can serve requests. So all nodes are created equal. I didn't mention that. And that goes together with high availability. We don't have a single point of failure. All nodes can serve requests. So the client chooses node V, and it wants to write the data 1. Node V, if you remember, performs the consistent hash function on the partition key of this row, and it determines which 3 replica nodes are responsible for this piece of data. Sorry. And these nodes are W, X, and Z. Okay, those are the 3 replica nodes. Nodes V sends along the message to the 3 replica nodes. The nodes successfully write the data and add it to their existing data, and they send an acknowledgement back to the coordinator node, to node V, saying the write was successful. For some reason, node X sent the acknowledgement, but say there was a network failure here, and the acknowledgement did not reach node V. What do you think would happen here? Would node V return a failure or a success, or would it do something else? If you can quickly write in the chat window what you think would happen. What happens with a replication factor of 3, consistency level of quorum, and only 2 out of the 3 replica nodes acknowledged the write request? What do you think will happen? So one idea is that it will succeed and then retry the write. Another is that it's a failure. Any other thoughts? Another idea is that it won't succeed and try again. Okay, so some of you are right. In this case, the operation would be successful because 2 out of the 3 nodes acknowledge the request, and the consistency level, which is important here, is set to quorum. That means that a majority of the nodes need to acknowledge the request, and 2 out of 3 did. So node V would return a success to the client, and later it would make sure that indeed the data was written. In the same exact example, if the consistency level here was all, and that means all 3 replica nodes need to acknowledge the request, in that exact same scenario, then node V would return a failure to the client. Okay, so this is an example of consistency level and how important it is. And again, there's no wrong or right here. This is an example of having to think about your application and about your data model for what you would want to choose. And there's a question, what is the strategy in picking the nodes, or is it random? Are you asking about picking the coordinator node that the client asks to write the data, or are you asking about which are the replica nodes? ACK stands for acknowledgement. So just acknowledging the request, and it's not a stupid question, and I'm happy that you asked it. So the question from before was about the replica nodes. So again, the way that the replica nodes are chosen is, if I go back to my previous slide, is they're chosen by using the consistent hash function. Okay, so the database runs something called the partitioner, which is a hash function on this data that's written. Say we call the row 1, and then according to the received hash, it knows which replica nodes are responsible for that data. Okay, great. So let's move forward. I talked about the different concepts: key space table, partition key, and the consistency level. I didn't really mention it, but the database works with multiple data centers. This is a bit more advanced, but the database is topology aware, and it runs on multiple data centers, and it's aware of where it's running. Now, there are a few benefits for doing that. One is simply performance. So say we have this topology with a data center in America, one in Europe, and one in Asia. So it would make sense to serve users from America with data from the US data center, right? Just because it's physically closer, and just because of physical limitation, I believe sending a packet from America to Asia is around 100 milliseconds, so that's quite a lot. It would make sense to serve a user from the data center that's closer to that user, and later asynchronously to update the other nodes that are further away, and then the user doesn't have to wait. So one thing is performance. Second reason, again, is high availability. So within a data center, the database is aware of different availability zones and racks, and it's very unlikely that an entire data center goes down. But even if that happens, the system can still be up and running and serve requests from other data centers. And we actually had something like this happen. I think it was Kiwi, one of our users. There was a fire in one of the data centers in Europe, and thousands of websites were unavailable, but Kiwi were able to still stay up and running without any downtime because they just switched to a different data center. And there's a question here that's also asking about regulation, and that's a good point. So the third reason to use multiple data centers and to be topology aware is for regulation reasons. So in some jurisdictions, maybe the government or whoever determines that data for a users of group has to stay within that geographical area. And then we can also define that, say that users from the EU will have all their data stored within the EU, and that data would not leave that geographical area. Okay, so again, I talked for quite a bit. Maybe let's do another poll question. So how much data do you have under management in the projects that you are associated with, just to get an idea? Is it less than a terabyte, between 1 and 10 terabytes, between 10 and 50, 50 and 100, or more than 100? If you can quickly answer in the chat window, how much data do you have under management in the projects you are associated with? So let's take a minute and answer that. Please answer in the chat window. Meanwhile, I will start this lab that I want to run later. Okay, so I see that for some people it's less than terabyte. Anyone managing data that's more than 1 terabyte here? Okay, so for the organization, between 10 and 50 terabytes. Okay, great. So let me move forward. And I talked about the partition key. And I only mentioned the clustering key. I didn't really explain how it works. So let me do that. The way that data is stored in ScyllaDB, and again, I'm reiterating this also in Cassandra and somewhat in DynamoDB and other databases, is according to the partitions. So what we see here is the partition key, and this is the PetChip ID, if you remember. And for each partition key, we have the data simply stored as a set of name value. So, in this case, it's the time and the heart rate and the values for the data, and they're stored sequentially one after the other for the given partition key. Now, the way that the rows are sorted within a partition is done randomly if you don't define a clustering key. But if you do define the clustering key, then it's defined according to that order. So in this case, what I'm showing you is a partition key, and the clustering key is according to the time. So if we have more than one value for a given partition, it would be ordered according to the clustering key, and that would make querying on the clustering key column very efficient, right? Because imagine what the database has to do when we query for a piece of data. It has the partition key, so it knows exactly where our data exists. It finds the partition very fast, and then within that partition, if the data is ordered, it knows exactly where the data that we're looking for is placed, or we need to read it, or we need to write it. So that's very fast. So the clustering key can be 0 or more columns. It's not mandatory, unlike the partition key that we have to define. The clustering key does not have to be defined. And by the way, in ScyllaDB and Apache Cassandra, we call it the clustering key. In DynamoDB, it's called the ordering key. Okay, so ordering key is probably a better name, but yeah, for historical reasons, we chose clustering key, similar to the name in Cassandra, but keep in mind that they mean exactly the same thing. Okay, let's talk a bit more about data modeling. So some of you mentioned earlier that you come from an SQL background. And here I have a very high-level comparison between NoSQL and relational database and how to create the data model. So typically in relational databases, and again, this is a simplification, but we first of all think about our data. We look at the different entities. We create an entity relationship diagram. We look at the relationships between the different entities. From that, we derive our schema. And finally, we look at our queries. So that's in relational. In NoSQL, there's quite a big difference. And the difference is that at the very beginning of the data modeling process, we have to think both about our data, but also about the application. So we have to consider which queries are we going to perform, how often are we going to perform them, what's the performance required. And instead of thinking about that only at the very end, we think about it at the beginning together with the data. And from that, we derive the schema or the data model. And typically, we iterate and see if this works and then make changes as necessary. Okay, so this is an important slide. Keep that in mind. Okay, so before I go further with the slides, I want to show you a quick lab. I am not going to run it for too long just because we don't have that much time. But like I said, we're going to be sharing with you by email a link to the slides and to the labs so you can run it yourself, and you have access to more labs in ScyllaDB University. So there is a question about the previous slide. Let me move back. Yeah, the question is, why is the model portion grayed out? And there's no real reason for that. It's just for design purposes. So that's how the slide was designed. It doesn't really mean anything. Okay, so let me go on to the lab. So what I'm showing you here is a platform that's called Instruct. And basically, it allows you to run a virtual machine within your browser. So it doesn't matter which operating system you're using. You don't have to worry about prerequisites or anything of that sort. And it just works. And let me full screen this. And I have instructions here on the left-hand side and my terminal here. And what I'm going to do is I'm going to start a 3-node cluster using Docker. Okay, so let me run this command. And what this command does, let's quickly go over it. By the way, can you see the font, or is it too small? The font size in the terminal, is it okay? Okay, if it's too small, just let me know. So what this command did is it started a 3-node cluster running on Docker, just because it's very simple to do. In production, you probably don't want to run on Docker, but yeah, that's a different topic. If you're thinking of doing that, then look in our documentation. There are specific instructions for how to run on Docker in production. But here we're just testing it out and playing around with the database, so it's completely fine. So what I do here is I run Docker. I give each node a name, node X, node Y, and node Z. And I provide the Scylla version. And this simply starts the 3-node cluster. And the next command that I'm going to run is called notool status. And I run it on one of the nodes. It doesn't matter which one, in this case, node X. And when I run it, I see the status of my cluster. So I can see that my cluster has 3 nodes. I can see their IP addresses, and I can see that they're up and running. So UN means up and running. If some of them didn't join yet, or there was a problem with one of them, then they would either not appear, or they would have a down status or another status. Okay, I can also look at the nodes, the logs of each node, but I'm going to skip that. And there are two main ways to interact with the cluster. One is using the CQL shell, which is what I'm going to show you right now. And to do that, I simply run, I provide the name of the node and CQLSH, and that connects me to that node. So now I'm connected to node X, and I can run commands and interact with my cluster. However, in real-world applications, of course, you typically don't work with a shell and you use drivers. We have drivers in different languages, most languages that you can think of, Rust, Go, C++, Java, and some others. So you can use the drivers, and there's an entire course in ScyllaDB University with examples for how to use each driver that you could just try yourself. Okay, so now I'm connected to my cluster. Let's move forward and perform some very basic queries, just so you see how easy it is. So I am again connected to my 3-node cluster. I create a key space, calling it my key space, very original. And if you see, just like in the examples in the slides, I define the replication factor to be 3. Okay, and that means that each piece of data is going to be copied 3 times. So in this case, each row will be copied to all 3 nodes. Now, using this key space, I can define a table, and I define a very basic table with just 3 columns. We have different data types, just like you would expect. In this case, I'm using user ID, which is an integer, and first name and last names, which are strings. And if you remember, we have to define the partition key. That's how the database knows how to find, write, or read data. And we define the partition key to be the user ID. Now that I have my table defined, I can insert data into the table. Yeah, let's look at this command. Insert into users, the table name, and I provide the 3 columns and their values. So it's very straightforward. I inserted 2 rows, and now if I read my data, then just as you would expect, I can see that my table has these 2 rows that were just added. Okay, I didn't mention it, but it's written here. When I use CQL shell, the default consistency level is 1. Okay, so because I didn't define any other consistency level, the consistency level that was used here is 1. If you remember, the consistency level means how many replica nodes are required to acknowledge a read or a write request for it to be considered successful. So what you're going to see in this lab, I'm going to stop here, but let me just show you the next part. So what you're going to see in the next parts of the lab is running different queries with different consistency levels. Okay, what happens when we use quorum or all, and what happens when some of our nodes are unavailable. Okay, so because we're using Docker, it's very easy to simulate a situation where a node is down. We just stop the Docker machine, and then we can see, yeah, I'm happy that you like Cartman. Then we can see what the database would do if some of the nodes are down when we use different consistency levels. Okay, so this is the high availability lab, and I'm going to provide a link to it in the email that you'll get probably tomorrow, and you can continue running it. But I want to go over some more material because we're almost out of time. Okay, so some data modeling guidelines. Yeah, some of the things that we want to try to achieve when we choose our partition key is even data distribution. Okay, this is very important. because we have a number of different nodes, and each node is responsible for part of the data, we want to avoid a situation where some of the nodes have a large percentage of the data, while other nodes have hardly any data at all. Okay, and how do we do that? Well, first of all, maybe the motivation. The motivation is that if it's not even, then some nodes would have a very high load, while others would hardly be working at all, and we wouldn't be making very good use of our resources, of our hardware, and yeah, that doesn't make a lot of sense. Let me go back to the lab because I wanted to show you one thing, which is Scylla monitoring. I didn't test this, so let's see if it works. Okay, it does. And I won't go into details here, but you see there's a separate tab called Scylla monitoring. This typically runs on another machine, and it connects to your cluster, and it can tell you how many nodes you have, how many requests per second are running right now, what's happening with each one of our nodes. And another important thing is that it can tell you if you have large partitions or hot partitions. So if you're running ScyllaDB in production, or if you're playing with it, be sure to also be running the ScyllaDB monitoring. Otherwise, it's really hard to understand what's happening in your cluster. Okay, so back to the slides. I talked about even data distribution. Now, how would we achieve that? Let me maybe give a negative example for how not to achieve it. So, yeah, this goes back to how we choose our partition key, okay? So, let's say that we're talking about people in the United States, that's our data, and a way to not do it correctly would be to choose, say, the state of each person as the partition key. So there are 50 states in the United States, but we're talking our data is people in the United States, and some states are bigger. They have a big population, say California or Texas or other states, while other states have much, much less people. Okay, so if we choose states of the person as the partition key, then some nodes, say the ones that work with the partition key of California or big states, would have a lot more data than other nodes that are responsible for the partition key of, say, I don't know, Delaware or other smaller states. Okay, so ideally we want to choose partition keys that would ensure that the data is evenly distributed. We want to achieve high cardinality, and basically that means that there are many different options for the values. So 50, the number of states, is quite low. A much better option would be user ID, which is typically unique for each user, and there are a very large set of values. So that would be a better choice for partition key. So that's even data distribution. Another point to, install the monitoring, I already said that. Before I move to collections, another point to keep in mind is the access patterns, okay? So in the very first slide about data modeling, I said that we have to think about our application at the very beginning of the data modeling process, and not just at the very end, like we do with relational databases. And the reason for that is that we have to think about which data we want to access and how often. Okay, so say we chose a partition key that has a good distribution of the data. All nodes have similar number of rows, but for some reason our application not only but accesses specific people way more often than others. So say our application only accesses people that are 80 years or older, or it accesses those people more often than others. In that case, even though the data is evenly distributed, we would still have nodes, the ones that are holding the data with people aged, say, 80 or over. So those nodes would be accessed way more often than other nodes. And again, we wouldn't have equal distribution in terms of the access pattern. Okay, so two things to think about. One is how much data each node is holding, and the second, the access patterns, how often we're accessing each node in terms of the data that it holds. Okay, we're almost out of time, so let me very briefly talk about a few more concepts. I won't go into detail, but just so you know that these concepts exist and that if you want to learn more about them, you can find the information. So collections, I talked about different data types that you would expect, like integer, string, and so on. But another data type is collections, and there are a few types. One is sets, lists, another is maps, and you can also use user-defined types. In the slides, you can see different examples. In some cases, it makes sense to use collections, and I won't go over it, but you can see different examples here and an explanation of the differences between collections. So basically, sets have a natural order, and data is, we just have one piece of data, so it's overwritten, while lists can have multiple copies of each piece of data, and you can define the order yourself. Welcome, Oliver. Thanks for joining. And are the slides not updated? Is it for everyone, or can you see the slides? Okay. I wonder why. Tell me if you can now see it. So now it's on collections sets. Now, yes. Okay, so maybe I have to move my mouse or something like that. Okay, so I mentioned sets and lists. Maps are more complex. For example, you can define a map of text and integer. Say you want to add a latitude, longitude, and altitude. You can do that. And we'll skip the poll. So those are collections. I know I ran through it, but know that it exists. And if you want to see the examples, look in the slides or on ScyllaDB University. Counters are a special type of column that allows us to, just like it sounds, it's a column that allows us to either read the data or increment or decrement the counter. And it does so in an atomic way, okay? So that's really important. The counter column offers a very high consistency, and that's useful. So it's very straightforward to use, but it does have some limitations. For example, the counter columns cannot be part of the primary key. So those are counters. User-defined types, I'll skip that. And time to live, let's take this as the last topic. So time to live is very useful because data tends to grow and grow. And when we hold a lot of data, especially if it's not needed, then we're wasting resources, we're wasting money. So when you create your data model, you can define TTL, or the time to live. And what that does is it defines that after a certain number of seconds, the data will automatically be deleted. Okay, so in this case, the table was defined with a time to live of 86,400 seconds. I think that's 10 days, but I'm not sure. And that means that after that number of seconds, the data will automatically be deleted and you don't have to worry about deleting it. Okay, you can see different options for changing the default time to live. By the way, whenever you update or insert new data to the table, then that updates the TTL for that piece of data. And the default time to live is null, which means that data is not automatically erased, only if you define it. There is a question if there's a way to push all data to S3. So I know that we're working on a possibility to do that, but I'm not sure if that is already available. So that's a good question, and I don't know. It might be ready, it might not. There's another question if those are big integer. I think big integers are separately defined. So by default, it's not a big integer. But again, that's a good question, and we can look it up in the documentation. So the question is, there's a question about TTL. Is it with a respect to a column value or absolute time? And that's a good question. The TTL can be defined for the entire table, and then it will automatically work for all the columns. But we can also have a table with different columns that have different TTL values. Okay, so both options are there and they're valid. And whenever we write new data, it will update the TTL. Can we use 10 years data retention? So yeah, I don't think there is any limitation on the time to live value. I wonder how much sense it would make for your application, but that's up to you, and I'm pretty sure that it's possible to do that. Last question, how is relation emulated multiple queries? So if I understand you correctly, Alan, you're talking about denormalizing data, and that's a really good question. Let me see if I have something on it. So towards the end, I added two topics here. One is materialized views and indexing, and the other is lightweight transactions. And they're more advanced. I could probably talk just for an hour about each one of them, but there is an entire lesson on each one of them on ScyllaDB University. So denormalizing data in NoSQL databases is a more advanced topic. It's possible to do, but it requires more work on the user side. And you can do that either with materialized views or with indexing. With that, I want to be respectful of your time. So let me go to the last slide. By the way, there are two more labs that are embedded here in the slides that you can check out. These are the links to Scylla University. We have a community forum where people ask questions or share how they're using the database, also for development or issues or feature requests. And this is the link to Scylla Cloud. And I hope you enjoyed my talk. Stay in touch. This is my email. We're also hiring. So if you're looking for work, shoot me an email. And thanks for joining. Appreciate it. And we will send you an email with the slides and all the links to the labs. Thank you, everyone. And thank you, Vered, for helping me host this.
Thank you very much, Guy. See you next time.